Hey everybody, welcome to the last week of class. Something on my keyboard here. Sure, let's see. Yeah, so I think it might have been you, Alejandro, who had asked that in one of the ways I get information for you guys. And I definitely, that's the first thing I was planning on doing today. So we can definitely go over problem 7 and also 8 and 10 because they're parts of problem 7 and 9. So we can definitely go over that. Let me give you guys the usual things. Here's the attendance and tutoring and the spring quarter evaluation, and here it is again. Well, let's go ahead and get started with a problem that is similar to problem number 7 here. Let me take a look. Yeah, oh yeah. Sure. Oh, sorry. What's going on? Okay. All right, what have I got here? We want to maximize. Sure, we can do something totally like that. Sure, depends. All right, so sometimes people, so this problem is written out very nicely, and he kind of just gives it to you, right? He says, suppose that x is greater than 0, and y is greater than or equal to 0 are real numbers such that 2x plus y equals 8. Compute P, the product of x and y as a function of x alone, and find the domain of P assuming that x and y are both greater than 0. I'm going to do a slightly different problem from a different book, and I'll read it to you just to kind of show you the difference in how these can be phrased, because I feel like this phrasing is pretty nice, and yeah, we can look at those too. So here's another way it might get phrased. So in this book here, the problem says find two positive numbers satisfying the given requirements. And let's see, I was going to do this one here. The sum of the first and twice the second is 36, and the product is maximum. So when they say the sum of the first and twice the second is 36, what they're saying is something like x plus 2y equals 36. Right? That's the sum of the first and twice the second is 36. And then we want to maximize the product, which is x times y. Also, this does have the same conditions that x and y are. They actually say positive in this book, and over in your homework, they're non-negative because they're greater than or equal to 0. Let's write that down. X and y are both greater than or equal to 0. Okay, so the way he phrases this, and I think it's a good way of phrasing it, is he first says, you can guess that right, we can look at 3 and 5 as well. Yeah, 3 is not too terrible. 5, we did one like 5 last time, but I can do another one like 5. So he says, compute P, the product of x and y as a function of x alone. So what the intention here is that after you've written P as a function of x and y, right, the product is x times y, right, which is literally saying the product of two things is the product of two things. We have to take our constraint, that's what this is the constraint, and we have to solve for, well, so it depends. Since we're trying to write this product as a function of x, right, that's the directions say, we need to solve this for y so that we can plug in y in terms of x and have this all in terms of x. So I'm going to solve this for y. Use a better pen. So solving this for y, subtract x, so 2y equals 36 minus x, and then divide by 2. So y equals 36 over 2 is 18. And x divided by 2 is just x divided by 2. So then I can take this expression for y and plug it in over here. So the product as a function of x is equal to x times 18 minus x over 2. And we could multiply it out, right? You could totally write this as it's 18x minus x squared over 2. Now, there is an additional part to this, which I think is worthwhile. And it says, find the domain of P, assuming that x and y are both greater than or equal to 0. So if we're talking about the domain of P of x, right, because we were thinking of P as a function of x, clearly x has to be greater than or equal to 0, right? That's already been stated. But there is a largest value that x can have as well, right? If x was too big, y wouldn't, like, let's pretend for, so here's an example. Actually, I was going to pick the right thing. Let's say x was 40. Well, x couldn't actually be 40. Because if x was 40, then y would have to be negative to make x plus 2y equal to 36. So 40 is outside of the domain of this function because of the constraint that x plus 2y has to equal 36 and x and y both have to be positive. So to figure out what the upper limit on x is, what we're going to do is we're actually going to take this. We're going to take what y is equal to in terms of x and say, hey, I know that y also has to be greater than or equal to 0. But then I'm going to replace y with this and say, oh, really? 0 has to be less than or equal to 18 minus x over 2. I can add x over 2 to both sides. So positive x over 2 is less than or equal to 18. And then multiplying both sides by 2, I get x is less than or equal to 36. So my domain here is x is between 0 and 36. So you can either write it as 0 is less than or equal to x is less than or equal to 36. Or I think he likes this notation where we say x is an element of the closed interval from 0 to 36. So x has to be greater than or equal to 0 because that's the condition we started with. X has to be less than or equal to 36 because if it was any bigger, y would end up being negative. We can't have that either. So this is how we would write out the product of x and y as a function of just x, either way. Now, I do think we should do part 8, or the second part of this question, which would be to use this to find the maximum value. Or specifically it says, yeah, compute the largest possible value of x times y. So let's do that next. So we want to maximize, right? We say one largest value. We want to maximize the product. Again, it's hard to do that when it's a function of 2 variables. So we instead write the product, like we did on the previous side, as a function of 1 variable. Where it was, I'm going to write it out the multiplied out way, 18x minus x squared over 2. Because now we know how to maximize or minimize a function of 1 variable. We take the derivative, we set it equal to 0, and find the critical values. So taking the derivative, I get the derivative 18x is 18. The derivative of x squared over 2 is 2x over 2, which is just going to cancel the x. So that equal to 0, so I've got 18 minus x equal to 0. So I've got 18 equal to x. And again, I'm not sure how much he cares about you showing it's a maximum, but in this case, so in the previous couple times, I've showed something was a maximum or a minimum by kind of using an altered version of the first derivative test where we see that it's increasing and then decreasing. But in this case specifically, since the domain is a closed interval from 0 to 36, we can use the extreme value theorem for absolute extrema and show that we have an absolute maximum when x is 18. So the way we do that is we look at our critical values, which is x equal to 18. We also look at our endpoints, which is x equal to 0 and x equal to 36. And then we plug those all into the original function. Now, when I plug into the original function, I usually prefer the factored form. So here's my factored form, which is x times 18 minus x over 2. And check out what happens. If I plug in 0, I get 0 times 18, which is just 0. If I plug in 36, I get 36 times 18 minus 36 over 2 is 18, I get 0. And this happens a lot when you have the endpoints of the domain for something you're trying to optimize. They often give you 0, which makes sense, right? Obviously, if x is 0, the product is going to be 0. Also, I think not too terribly hard to see, if x is 36, then y has to be 0, so the product is going to be 0. And then you have the one critical point in the middle, which not always directly in the middle, but this one happens to be right in the middle. Where if you plug in 18, I don't know what that's going to be, but it's definitely going to be positive. It's going to be 18 times 18 minus 18 over 2, which is 18 times 9, which is 9 times 9 times 2, 162. So not only does this show, so this, oh, how do you get 0 when you plug? So I get 0 when I plug in 36 because although this part was 36, this part was 18 minus 36 over 2, and 36 over 2 is 18, and 18 minus 18 is 0. It's because, it's, another way to think about it is that the product is x times y, right? When x is 36, y has to be 0, and then 36 times 0 ends up being 0. So again, using the stuff we know about absolute extrema or global extrema, this shows that we have an absolute maximum at x equal to 18 with a value of 162. Because we plug in the critical points, we plug in the endpoints, and of the three values, 0, 0, and 162, 162 is definitely the biggest. So we have a maximum product of 162. Sometimes, a lot of the time, we'll say, people instead ask you to find the x or y values that lead to the largest product. In this case, the answer, if the question was that, would be x would be 18 and y would be 9, right? Because we could find the y value would be 18 minus 18 over 2, which is 18 minus 9, which is 9. Oh, sure, of course, yeah. Thank you for asking. Here's the attendance post and tutoring. Should we do another one like this, where it's kind of just like numbers? I don't mind doing another one like this. Okay, cool. Let's see. One that's a minimum. Okay, where'd my pen go? Where'd my eraser? Where'd my eraser go? It's way over here. Sorry. So it's all over the place here. Which eraser is my good eraser? This one. Okay, so let's say similarly, we have two numbers, both positive, and we know that the sum of, I want to make it terrible, not really. Let's say the sum of the first and 3 times the second is, let me think for 1 second. Let's say 36 again. 36 is a good number. We want to maximize the product. So I'm going to do this one slightly different. I want, instead of finding the maximum product, although we'll probably also do that, the question we're going to ask is to find the values of x and y, or the numbers, I should say, but let's call them x and y. The values of x and y that maximize the product. And we'll do all the same sort of steps that he is asking in question 7. So step 1, I'm mapping to step 1. He's already, so here's our equation. X plus 3y equals 36. Yeah. And we're trying to maximize the product, which again is just x times y. Just like in the previous problem, we're going to write this product as a function of one variable x by taking this equation and isolating y, so that we can then plug in y equal to some x stuff into y here. So we take this and we'll solve for y. So we got 3y equal to 36 minus x. And I'm divide both sides by 3, so that y equals 36 divided by 3 is 12 minus x over 3. And I'm going to plug that in here. So the product as a function of just x is going to be x times 12 minus x over 3. Okay, so let me ask you guys. I'll show the domain, but I want to kind of ask you if we can just puzzle it out. Clearly, what's the smallest x can be? X has to be bigger than or equal to what? Yeah, 0. Definitely, right? Because they told us that in the beginning. Okay, so let me ask you guys. If y has to be positive, or I should say not negative, right? And x plus 3 times y equals 36, what's the biggest x can be where y is still going to be 0 or positive? How big is x allowed to be? Could x be 30? Sure. Because if x was 30, y would be 2. And 30 plus 6 is 36. Exactly. The biggest x could be is 36. And you can kind of see this. I mean, there's actually a couple ways to see this, right? You could say, right, 3. Well, in fact, it's really just coming from over here, right? From right here, right? This has to be greater than or equal to 0, which means that 12 has to be greater than or equal to x over 3, which means that 36 has to be greater than or equal to x. So that's where we're getting that from. So our domain here, actually exactly like the previous problem, is still x between 0 and 36. So you can either write it this way, or we can write it as x is an element of the interval from 0 to 36. Also, here's the attendance again, because I think I heard one person come in after I posted it. So here's our function, p of x equals x times 12 minus x over 3. And here's our domain, between 0 and 36. And so let me actually graph this function for you guys, because I think it's worth seeing the graph. And this just, let's squeak it in. Tighten this up a little bit. So our function, p of x, is x times, what is it, 12 minus x over 30? And our domain is x between 0 and 36. And here's what it looks like. Right, this is just a parabola. I can multiply it out and get 12x minus x squared over 3. It's actually more helpful to leave it like this, though, because leaving it like this, I can see that my intercepts are 0 and 36, right? If I plug in 36 for x, 12 minus 36 over 3 is 0. And it's definitely downward opening because it's 12x minus x squared over 3, right? I have a negative coefficient on x squared means it opens downward. So it looks something like this. And I shouldn't really extend the arrows because it ends there. So really I should just have that. So this is p of x, this is x. And I think it's, with the graph, I think it's not too hard to believe that, oh yeah, it's definitely going to be, the product is going to be 0 at 0, it's going to be 0 at 36, and then somewhere in the middle you're going to have a maximum product. Probably actually right in the middle. It usually happens for parabolas. If you know where the x-intercepts are for a parabola, you know that the vertex occurs smack dab right in the middle of those two. We can still use calculus, and we should use calculus to figure it out. So my function p of x is 12x minus x squared over 3. My derivative is 12 minus x squared over 3 is 2x over 3. So that equal to 0. Solve for x. 12 equals 2x over 3. Multiply both sides by 3 halves. 3 is canceled, 2 is canceled. 12 times 3 halves is 36 over 2, which is 18. And then we could either do what we did before and observe that p of 0 is 0, p of 36 is 0, right? So those are the endpoints. And then p of 18 is some positive value. It's going to be 18 times 12 minus 18 over 3, which is 18 times 6, which is 108. Or if you prefer, you can use the first derivative test for absolute extrema and say, well, we're on the interval from 0 to 36. We have one critical value at 18. we pick a number between 0 and 18, like 1, the derivative, right, not the original function, if I plug in 1, p prime of 1 is 12 minus 2/3, which is definitely positive. Pick something bigger than 18, like 30. P prime of 30 is 12 minus 2 times 30 over 3 is 60 over 3, which is 20. 12 minus 20 is negative. So it's going up and it's going down. So I have to have a maximum of 18. So to answer the final question, the values of x and y that give us a maximum product are x equal to 18 and y is equal to, oh, let's go back and look for y. So usually if you're finding the things, I need to WD-40 this thing up a little bit. If they ask you to find like the dimensions or x and y, if you're trying to find y, you usually want to go back to the place where you have y equal to something. So y equals 12 minus x over 3. So y equals 12 minus x over 3, or x is 18. So 12 minus 6 is 6. And that would be the answer here. So the x and y values would be 18 and 6. The maximum product would be the product of those two things, which is 108. But it's really important, especially with optimization, that you clearly answer the question being asked. Because sometimes they'll ask for the dimensions, sometimes they'll ask for what is the maximum volume or what is the minimum surface area. So make sure you're really paying attention to the thing they're asking for. Okay, let's look at another one. Let's look at one more like 9 now. I know I've got lots of examples of that. Let me pick a good one. Actually, I've got this one over here. So we'll do a couple of those too. But I should say, where'd you go? Generally, when you're thinking about optimization, it's all about the setup. I mean, it's also about finding the derivative correctly and finding your critical values, but the setup is pretty vital. You guys are all doing all right? By the way, today is my wedding anniversary. We've been married for 13 years, yeah. 13 years today. The day the world is starting to open back up, kind of, although not for me. I am staying now. Thank you for the congratulations. Appreciate it. So let's see here. So usually this next type of question that's like number 7 is phrased more concisely. I think Sanders writing, like the way he's writing questions are really good here. He's trying to get you guys to really think about it. But I'm going to show you what you'd probably be stuck with from other people on the test. So someone might say something like, oh, where'd you go? Sorry, let me find the question here. Find the point. Actually, point is usually more accurate. So find the point or points. There's sometimes more than one on the graph of y equal to x squared. Closest to, let's do the easy one first. Yeah, closest to 3, 0. Closest to 3, 0. So that's usually how you're going to see a problem more like, thanks for the congratulations, guys. I appreciate it. It's pretty great. I love my wife. She's a wonderful woman. So if we look at problem 9 here, he's definitely spelled it out for us again. So let xy be a point lying on the graph, y equal to the square root of x. Let d denote the distance from xy to the point 1, 0, or we're doing for our graph, whatever. Find the formula for d squared that depends on ln x, which is, so he's really making it this much better. So let me draw our thing. So here's our graph, y equals x squared. And we're trying to find the point. So we're going to call the point on our graph x comma y. And I probably draw it. It doesn't matter where you draw it, but I'm going to make it a little bit nicer. Let me go right here. Here's x comma y. And over here is the point 3, 0. And if we're trying to find the point on the graph that is closest to 3, 0, what we are in essence trying to do is minimize the distance between our unknown point here and the known point 3, 0. So we are trying to That distance there, we're trying to minimize that. So the first, and that's usually how this problem starts, is you're trying to minimize the distance d. So let's write an equation for the distance between the 2 points. And again, I feel like it doesn't look very clear on the screen. That's x, y, that's 3, 0. Let me write it a little bit nicer. I'm seeing a large equal error. Let me actually move this over. Let me just minimize this, actually. That way it'll be less glary. That's way better. Okay, at least for me. So the distance formula between 2 points, right, is going to be the square root of the difference in the x's squared. So it's going to be square root of x minus 3 quantity squared plus y minus 0 quantity squared. And then he's already gone ahead and made this even nicer by saying, well, look, instead we're going to look at the distance squared because it's easier to deal with and it gets us the same result. So if you're ever trying to minimize the distance between two things, you can always just say, instead we're going to minimize the distance squared. It will always give us the same result, which is great. If you care, well, I'll say this in a minute. There is a reason why it works, and it's really kind of nice, but you don't need to know the reason. So if you guys want to see the reason in a minute, I'll tell it to you, but if you don't, it's fine. So here's our distance formula, or sorry, our distance squared. It's just this without the square root. So it's x minus 3 squared plus y squared, right? Because I simplified y minus 0 to y. Now, I will say, he's also said, sorry, I remember where my notes can go. He has also said, find the formula for d squared that depends only on x. So just like the previous problems, we're trying to write the distance squared as a function of x. And clearly, our distance squared is a function of x and y. So we have to replace y with something that it's equal to in terms of x. Now, in this case, it's not that we have like the two things adding up to something. It's that we know this point is on this graph. So we know that if x, y is on this graph, y has to equal x squared, right? That is the function that we are on the graph of. So what we're going to end up getting is that the distance squared as a function of x, which I know it's kind of weird, but it's probably fairly standard, is going to be x minus 3 squared plus x squared squared. And now we've written it as a function of x. And I don't think he asked us about the domain in this one because there isn't really a domain restriction. Let me double check that. Yeah, no domain. So here there's no domain restriction, right? Because if you're on this graph, you could be anywhere on this graph. X could be anything, and Y could be anything non-negative. Yeah. Okay. So let's go write this on the other side, because then we're going to do the second part, which is doing the minimization. And then we'll do a second part too. So we have the distance squared as a function of x is x minus 3 squared plus x squared squared is x to the 4th. It was plus, right? Yeah. Okay. And we're going to try and minimize this. So we're going to take the derivative. This looks funky. Take the derivative. Derivative x minus 3 squared. You could have multiplied this out, but I kind of thought it was just going to be easier to take the derivative without doing that. So I'm going to say I've got some stuff squared. The derivative is 2 times my stuff to the first times the derivative of my stuff, which is 1. So really, there we go. Plus the derivative of x to the 4th is 4x cubed. Set that equal to 0. I'm worried this might not come out very nice, but sometimes it happens. So let's say, okay, here I've got 4x cubed plus 2x minus 6 equals to 0. So usually this would kind of be terrible. We're lucky though, in that at least I'm lucky in that I can see one of the solutions right off the bat. I can see that x equals to 1 is the solution. If I plug in 1, you get 4 plus 2 minus 6, which is 0. Usually you won't get a cubic that you have to solve, but if you do happen to have that, there's usually an easy solution to see. So I know that x equal to 1 is a solution. But there could be another solution. So the way I have to check is I actually have to do the polynomial division to see what's left over. You could do synthetic. I'm not a fan of synthetic in this context. So I'm going to do the polynomial division. Say x minus. So the rationale here is that if x equals 1 is the solution, then x minus 1 is a factor. So I'm going to divide by x minus 1 to see what the remaining quadratic is. So I've got 4x cubed plus 0x squared plus 2x minus 6. X multiplied by 4x squared gives me 4x cubed. And 4x squared is minus 1 is minus 4x squared. Subtract. 0 minus 4x squared is positive 4x squared. I'm going to go find the AC. It's really hot in here. Okay, sorry about that. And then bring down the 2x. And then x times 4x will give me 4x squared. So 4x times x is 4x squared. 4x times negative 1 is negative 4x. Subtract 0, 2x minus 4x is 6x. Bring down the minus 6. And this last step should go in perfectly. X times 6 gives me 6x. Take it 6x. 6 times minus 1 is minus 6. And those subtract perfectly. Remember, my remainder is 0. Now, I'm not dumb, but I'm a little dumb in that I totally could have factored out a 2 before I did anything else. That might have been smart. Oh well, sometimes we miss the obvious things. So here's what I can say. This polynomial, 4x cubed plus 2x minus 6, can be factored as x minus 1 times this, 4x squared plus 4x plus 6. Which I could totally factor out a 2. I'm left with 2x squared plus 2x plus 3. And then, so what we would have to do is we'd have to see if there were any more solutions. The way we would do that would be by checking to see if this quadratic equation has any more solutions. It does not. And the way I can see that is by looking at what the quadratic formula would give us. It would give us a negative in the discriminant. If I was trying to solve 2x squared plus 2x plus 3 equal to 0, and I started using the quadratic formula, my solution would be negative b plus or minus the square root of b squared, which is 4, minus 4 times a, which is 2, times c, which is 3. And right there, I would stop. Well, maybe I'd write the rest, right? Because I can see that the inside of my square root is going to be negative, which means there isn't a real solution. So for this problem, the only solution is x equal to 1. Now again, I feel like we should go back and reread the actual question because that might not be the actual solution one right now. So I look back at the original question. It said, find the point or points on the graph of y equals x squared closest to 3, 0. So it's not just that I have to find x equal to 1, I also have to find the y coordinate. The y coordinate should be easy because the graph is y equals x squared. So if x is 1, y is also 1. So the point is 1, 1. That is the closest point on this graph to the point 3, 0. Let me do one more variation on this, and then we will look at problems 3 and 5. So the other question we could ask, the other question I want to ask is actually the same question. Instead of the point on the graph that's closest, the point on the graph of y equals x squared closest to 3, 0, I want to find the point that's closest to 0, 1. So it's going to be pretty much the same work, just a little bit different. So, also I'm going to try and get some, sorry. I don't remember. Is your guys' final, I feel like I asked you this already, but I don't remember. Is your guys' final quiz cumulative or not? So is it cumulative? Yes? Okay, great. Then I will try and post a final review of sorts that isn't too long, so I don't think your quiz is going to be too long, just to give you some practice. I do also intend to post a quiz for you guys. I don't know if I told you this, but I definitely told other classes. The quiz this week is totally optional. Everyone will get credit regardless of if they do it. But if you have the time and you want the feedback, you should totally do the quiz. I know I haven't posted it yet because I haven't written it yet. We'll get it written and posted today. You'll have as much time as you want on it. But it's just going to be there for you to do if you want to. If you don't, you can still look at the solutions I'll post up later in the week. But that will be there if you want more feedback. Oh, what day is the final quiz due, Allison? Okay, cool. It gives you guys more time. Good to know. Let me actually write that down for myself real quick, just because I'm trying to figure out my finals week schedule, and that is good to know. Oh yeah, that's way. It was like due on the 6th before. Okay, that's a big difference. All right. Okay, so let's do this and then we'll do this one. So if I want to find the point of the graph goes to 0, 1, again, I'm going to do the same thing. I'm going to find the distance equation. So once again, the distance. Oh, sorry. I feel like I've done 0, 1. So now I'm over here, right? 0, 1. Now, I think it's pretty clear, or I think it's maybe clear. There's going to be 2 answers here. Because there's going to be a point over here, and there's also going to be some point over here that are both going to be closest. So it might end up being 0, 0. I don't know. We'll find out. So the distance formula from my point x, y to 0, 1 is the square root of x minus 0 squared plus y minus 1 squared. Of course, we're going to square both sides because we'd rather do the distance squared. So the distance squared is just x minus 0 squared is x squared. Y minus 1 squared I'm going to leave as is for the moment. And then finally, I'm going to plug in y equal to x squared, right? Because that's the graph that we have to be on to get my distance squared equal to x squared plus x squared minus 1 squared. And we could multiply that out. Again, I don't think it's really necessary or actually really useful. I think it's better to leave it unmultiplied out. I could be wrong about that. We'll see. So let's write that down on the other side. I'm kind of fast so we can get to the other side. That sounds, yeah, it's really not good sounding. Okay. So the distance squared, again, was x squared plus x squared minus 1 quantity squared. Now we're going to take the derivative of that. Derivative of x squared is 2x. Derivative of stuff squared is 2 times my stuff to the first times the derivative of stuff, which is 2x. This is going to be a little bit messier. So let's take a look. So here's what I see right off the bat. I've got a 2x here and a 2x here. I could factor that out. Instead of setting this equal to 0, factoring is usually the thing I'm really trying to do the most. Let's factor out a 2x. I'm left with here a 1, and here a 2 times x squared minus 1. So let's see, I get 2x times, this is going to be interesting. 1 plus 2x squared minus 2. So I end up with 2x times 2x squared minus 1. So here's what I end up getting for my 3 critical values. I get x equal to 0, because obviously if I plug in 0, it's going to give me 0. And then I have this part equal to 0. So if I have 2x squared minus 1 equal to 0, 2x squared equals positive 1, x squared equals positive 1/2, x equals plus or minus the square root of 1/2. So then we have to ask ourselves, okay, which of those is closest? Well, the easiest way to do this is not using the first derivative test, it's using just the fact that, so if we think about this, there's an infinite number of points we can plug in, right? But you can only be close, you can't be like, you can get further and further away, but you can't get closer and closer. So whichever one of these gives us the smallest distance or distance squared is going to be the closest point. So if I plug in x equal to 0, what do I get for the distance squared? Well, the distance squared is going to be 0 plus 0 minus 1 squared, which is just 1. If I plug in the square root of 1/2, right, positive or negative, shouldn't matter. I'm going to kill myself here. We plug in plus or minus the square root of 1/2. The square root of 1/2 squared is going to be 1/2, whether it's positive or negative. And the square root of 1/2 squared is going to be 1/2 minus 1 squared. So you get 1/2. 1/2 minus 1 is negative 1/2. Squared is positive 1/4. So I get 3/4, which is smaller than 1. So here's the interesting thing. These 2 points are the closest, and then, sorry, I got a little dizzy. So these 2 points at negative 1/2, sorry, negative square root of 1/2, and positive square root of 1/2 are closest, and then these points actually get further away, but then this point is actually closer than these points again, which is kind of weird. Unless I'm doing something dumb. Sure, there's something dumb. It's always possible there's something dumb. I don't think so, though. Yeah, interesting. It's kind of weird. But yeah, I'm intrigued. I'll have to look at this problem more on later on. It's kind of neat. So to find the points, we would say, okay, x is plus or minus square root of 1/2, and y is the square of that, which is just 1/2. So there's 2 points: negative square root of 1/2, comma 1/2, and positive square root of 1/2. Okay. So let's move along to questions 3 and 5. We got time. We got 10 minutes. We got enough time. So question 3 isn't too bad. It's really just repeated use of L'Hopital's rule. So, and the thing that I think might be throwing people off with that one is you can't just L'Hopital's rule it until you get to an answer. You have to do some algebra at some point. So let me give you a slightly different version. Let's say we have the limit as x goes to infinity of, what am I going to do? Something not too terrible. 3, don't be dumb, James. 3e to the, I want to make it fun though. 3e to the x plus 2x squared over 2e to the x plus 6. So this is kind of like those rational function ones we did, where it's really just like the highest degree terms that matter. In this case, it's the biggest thing that matters, which is e to the x. And since this e to the x and this e to the x are essentially the same power, it's the quotient of their coefficients that's going to end up being the answer. Here's the work, though. Using L'Hopital's rule, I get the limit as x goes to infinity. The derivative of 3e to the x is 3e to the x. Oh, sorry. I should have started off by saying I have an infinity over infinity type. If the top is definitely going to infinity, so is the bottom. So I can use L'Hopital's rule. So the derivative of the top is 3e to the x plus 4x. The derivative of the bottom is 2e to the x plus 0. Still an infinity over infinity type. The top is going to infinity, right? Infinity plus infinity, the bottom is going to infinity. So I use L'Hopital's rule again. The limit as x goes to infinity of, take the derivative of the top, you get 3e to the x plus 4. The derivative of 2e to the x is 2e to the x. At this point, you actually could do something and finish the problem, and I'll show you that in a second. But I feel like there's something else I said before I was going to show you. Oh, yeah, that wasn't that important. Instead, it's probably easier just to use L'Hopital's rule one more time. Let's say I got, let's see, the derivative of the top is 3e to the x plus 0. The derivative of the bottom is 2e to the x. But now the e to the x's can cancel, and I have the limit of a constant. And the limit of a constant is just the constant. So that's how that one works. Alternatively, at this stage here, if you wanted to, you can break this up into 2 separate fractions and say it's the limit as x goes to infinity of 3e to the x over 2e to the x plus 4 over 2e to the x. And then this one, the e to the x cancel, so you get 3 halves. And this one, the denominator is going to infinity, so this one goes to 0. So you get 3 halves plus 0. But that would be more likely or more partial to doing it this first way, because it just seems easier. Yeah, let's look at a problem like problem 5. So we did do one like this in class on Friday. with just a square root of x, I would encourage you to go back and look at that example. I think we did it relatively early on in class, but I can't remember, to be perfectly honest. But let me give you guys another example. Ooh, I want to make another example that's not going to be super tricky, James. I think. I can make it a little tricky. Sure. Make a, so I'm going to make one that it's, I don't think this, well, we'll do this one and then we'll see. Let's have the limit as x approaches 2, 3 from the right of the square root of 2x minus 6 times the natural log of 2x minus 6. And first and foremost, well, yeah, it's important to recognize that this is an indeterminate form. If x is approaching 3, 2 times 3 is 6, 6 minus 6 is 0. And if x is approaching 3, 2x minus 6 is approaching 0, and the natural log of 0 is approaching negative infinity. This is a 0 times the infinity type, and that is indeterminate. And whenever you have a product like this where it's 0 times some sort of infinity, you always want to bring one piece down to the bottom as its reciprocal, so that you then have a fraction that you can use L'Hopital's rule on. And you almost never bring the natural log down to the denominator. So I'm going to rewrite this as the limit as x approaches 3 from the right of the natural log of 2x minus 6. I was going to get x squared. Oh well. Over 1 over the square root of 2x minus 6. Because when you bring something down to the denominator, you're dividing by the reciprocal, so it doesn't change. And then I would personally prefer to rewrite this so that it's easier to differentiate the top and the bottom as the natural log of 2x minus 6 over, this is, I'm going to rewrite all of this as 2x minus 6 to be negative 1/2. Okay, and now we can use L'Hopital's rule because we do have an infinity over infinity type. The top is going to infinity because when the argument of a logarithm gets closer to 0, the logarithm goes to negative infinity. And the denominator here is 1 over the square root of 0, which is blowing up to infinity as well. So now we're going to use L'Hopital. I'm writing the L'(h) so that the person reading my work knows I'm using L'Hopital. I'm going to do the derivative of the top. So actually, first I'm going to write the limit because I'm still taking the limit of this expression. I'm going to do the derivative of the top. The derivative of the natural log of 2x minus 6 is 1 over the stuff times the derivative of the stuff. The derivative of 2x minus 6 to the negative 1/2 is negative 1/2 times my stuff to the negative 3/2 times the derivative of that stuff, which is 2. And right off the bat, I can make this 2 and this 2 cancel. I mean, there's lots of 2's that get canceled, but I'm going to cancel those 2's. So then I'm going to rewrite this. And this is where things get a little bit messy. So limit x goes to 3 from the right. I'm going to write this as 1 over 2x minus 6. And then dividing by this, I really want to multiply by the reciprocal. So instead of dividing by negative 1/2, I'm going to multiply by negative 2. Or negative 2 over 1 if you really want. Instead of dividing by 2x minus 6 to the negative 3/2, I'm going to multiply by 2x minus 6 to the positive 3/2. And then 2x minus 6 to the 3/2 over 2x minus 6 to the first, I can cancel and be left with a 1/2 power there. So I have the limit as x approaches 3 from the right of negative 2 times 2x minus 6 to the positive 1/2. And then when I plug in 3, 2 times 3 is 6, 6 minus 6 is 0, 0 to a positive power is 0. So I get negative 2 times 0, which is just 0. 0 to a positive power is always fine. 0 to a negative power is undefined. So do be careful about that. So I think that's all I've got for you guys for today. Don't hesitate to send me a message if you've got questions. I will definitely try to get things posted up today. I had a less productive weekend than I intended to, but I will try and get a quiz posted for you guys that, again, is totally optional. You can do it if you want to. I will give you the feedback on it. But if you just want to look at the quiz and then look at the answers later, that's also fine. And I will post up a final review of sorts for you guys to do as well, which again is not due, but I'll post up the review and the solution so you guys will have more study materials to have for your final. And I guess I'll look at Sanders. Does he have a practice final up somewhere? I imagine he does, but no, he does not. Okay, well then I won't look at his practice final and try to see. If he does post up a practice final, shoot it over someone email it to me, because sometimes I'm not always able to access everything that they post. But if he does post something, let me know, and I will use that as kind of a guide of sorts to make my final review more in line with what you guys are doing in class. Okay, good seeing you guys. You're all very welcome. Oh, one last thing. We don't have, as a reminder, I know I said this last week, we don't have class on Friday, like not officially. You're not required, but I'm going to still hold class at the same time, which will be more like office hours. So you guys just ask whatever question. I mean, it'll be probably just like class where you guys can ask whatever questions you want. But you are officially required to be here because it is, right? We don't have class on Friday. That's when finals start. So if you can't be here on Friday, totally understand. But if you want to show up on Friday, you're welcome to come and ask whatever questions you want. Okay, that's all I got for you guys. I will see you on Wednesday.